Hello friends and dear viewers, in this particular video presentation I have found it quite reasonable and necessary to thoroughly discuss and elaborate on the process of calculating a specific field by utilizing the time-independent Maxwell equations, especially when we already have a field readily available at hand. I genuinely believe that it may initially seem like a rather daunting and complex formula. When I put myself in your shoes, I felt that this equation might scare you, so I chose to shoot this video separately. In the third video, I mentioned this in the long video, but since I talked about many things in that video, and I thought people might be a bit reluctant, if not very reluctant, to listen to all of them separately, because the video is long, I thought at least we should provide a brief version here, so that you might not hesitate to learn this. Therefore, without further ado, the time-independent form of Maxwell's Faraday equation, and since Maxwell's Ampere equation is related to the magnetic field, I can easily remember its name as the Ampere equation because I know it relates to electric fields and charges. When I think of charges, Faraday comes to mind, so I can easily recall that this is the Maxwell-Faraday equation. Now, when we pull this to this side, we actually need to release the hash because we reach its hash through the cross-product operation with the Nabie laboratory, which we call TREV, relative to the field we have. Similarly, when we leave the electric field alone here, the magnetic field we have will enter this cross-operation. What we have will enter here so that we can reach what we do not have. What we have will enter here, and we will reach the electric field that we do not have. So how do we apply this? How is the cross-operation applied here? I want to talk a bit about this, to be honest. Now, in that video, for example, we explained that this is the incoming field, right? This part where we will perform the operation is coming towards this side. And since this perfect connector is a superconductor, this incoming field is generally represented as EI, where the I stands for incident, meaning the incoming field. Now we have EI, and since this is a wave, there must also be HI here. But this EI can have three components. Here we can solve this question in Cartesian coordinates. There must be at least one of the x, y, z components. Since the question is given here, I understand the amplitude is important for us. The one that gives the amplitude here is E0, which is E0. I also see that there is a z direction next to E0. Therefore, since the amplitude is in the z direction, I can understand that it is the EZ component. Since this is the direction of propagation, I can understand that it is in the positive y direction because x is here. If it had just given me this and that, I could easily write it just by looking at the shape. Later, if there is an electric field here, there must also be a magnetic field, and I do not know this magnetic field. This magnetic field can have multiple components, but in such questions, it generally extends in one direction. However, we cannot know whether it extends in the x, y, or z direction. We may not be able to know which direction it extends honestly. Therefore, we do know this. Since these will propagate perpendicular to each other and there is an EZ component here, I predict that one of these will likely come. We do not leave this as a guess. By not leaving it as a guess, since it gives me which of the Maxwell equations we have here for the incoming electric field, I can then find the incoming magnetic field for the incoming electric field. By using the Maxwell equation, at the same time, after solving Helmholtz, now we are not concerned with Helmholtz here. In the previous video, I explained the logic of Helmholtz. After calculating both the incoming field and the reflected field with Helmholtz here, it is written as reflected. It is represented as R. There is also T normally. It is called ET. Transmitted meaning exceeding this, but in this question it will not pass because it is a perfect conductor. Right now we are not concerned with transmitted fields, meaning the fields that are carried. Only reflected fields will occur if they are formed here. After solving with Helmholtz, let's say you found ER. After finding ER, if a wave is propagating in this direction, it is likely that it must come to E raised to the power of plus jk. You can find this from Helmholtz. If there is indeed an outgoing electric field, the magnetic field must also be in this way, But I cannot know right now. Is there an EZ component? Is there an X component? Is there a Y component? It is found from Helmholtz. After finding it from Helmholtz, you can also find HR using the Maxwell equation here. So the essence of the matter is this. I will now do an example. Just this specific question. How do we solve the magnetic field in this part when there is an electric field component of the incident electric field? I want to teach you about it, right here. If we learn this, we will have at least completed one more step. In the later, long problem solutions, we had already explained both Helmholtz and the boundary conditions I initially described. Once we complete Maxwell, on top of the boundary conditions and Helmholtz, the main concepts are established. Therefore, we want to learn in a short video. Here. Of course, as I talk about these, the video gets longer, so I will move on quickly. Here, for example, if we have a component of an incoming electric field, there must also be a magnetic field present. Why must there be? Because they were moving perpendicular to each other. As you may recall, the electric field and the magnetic field, along with the direction of propagation, are perpendicular to each other. In fact, since the direction of the electric field is in the direction of Z and the direction of progression is in the direction of provocation, that is, in the plus Y direction, I predict that Hajix will most likely come, since we know the rule. We can understand this because we know the rule that they are mutually perpendicular. I have to say that to better understand the logic of these, you might say, get to the process quickly. But if I say these things, it will settle more comfortably for you, he said. That's why I'm talking. Sorry for that. Now let's try to learn how to use this equation right away. For example, I have E and I. In what form do I have them? E is extending in the Z direction. So if this is a Z direction, let's draw it like this. If this is the Z direction, this electric field is a combination of X and Y. Let's call it rho. It extends like this. And there is an amplitude extending in the positive Z direction, which we can say has a magnitude of E0 if we take the maximum. If I say I will try to extract the incoming component of the magnetic field from this area, let me take this equation again, and which one will we apply? By the way, I'm asking you, I said we can input it into the cross-product operation. Now, since we have the electric field here, which one will we input into this equation? Of course, I will input this one. Not that one, because my goal is to reach this. Therefore, I will reach this, so let me take the equation above. I have used this one. It would be sufficient for you to understand if we solve one of them. I will solve this, and let's see how it will turn out. Look, I took the equation here. I'm starting here. Look, it's not written like this. I say it equals. Let's write it like this. I say that hash equals, friends, and I write it down without hesitation. I say that there can be three components. In things I don't know or am trying to find. In the EX direction, I have the hash X component. In the EI direction, I am currently only opening this. I haven't moved on to this part yet. I say that I have the hash E in the EI direction and the hash in the EZ direction. Later on, I move on to the this equals part of the operation, and write as follows. -1 over J, omega, nu. The nu here, we call it a gyroscope when solving in air. In this question, there was a solution in air. Therefore, you can actually take the gyroscope here. It doesn't matter at all. It will give you extra. If it says I'm doing it in a different area, not with nu0 or epsilon 0, it will say nu1 or nu2, or it will provide these values if you are solving a numerical question. Here we can take nu0. Let's take nu0. Let it be air. And now how do we perform the cross-product operation? I have prepared the electric field this way. Now this has to be vectorial. As you know, the cross-product operation is performed on vectors. This is a vector. This and the cross-product operation represent the vector direction of our electric field. Let's see. If this is the field we have, then these are the fields we are trying to find. Now this cross-product operation is done with the determinant part, friends. Now let's show how this is done. I am showing you like this now. Let's say we wrote the hash like this again. You already know that H is now this, so I won't write it again. -1 over J, omega nu 0. For the del cross E, you do it like this, friends. You open a determinant, like this. Let's draw it more neatly. I opened a line of determinant like this. In the determinant line, first, depending on which coordinate system you are working in, since we are currently working in Cartesian coordinates, you write the direction vectors properly in the first row. Essentially, if we say it like this, the first row contains the direction vectors, and, in essence, the second row actually should be like this. Here, the first element of the first cross element, and here, the second cross element is written. Basically, fundamentally, essentially, in essence, 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 basically, fundamentally. By element I mean which component, the elements of the nabla operator are written here, while the components of the electric field are written here. I will write the first element here. What was the first element, if you remember? It was the derivative. It was the derivative with respect to the ground. Therefore, what is the relevant derivative for x? Del over del x. What is it for y? It was del over del e. If you remember, that was the expansion of the nabla. So, with respect to the ground, this cross, this cross, this was normally, if you remember, and del over del xi. Now after writing this, who is the second element? Let's do it this way, so it is clearer. This is the second element. This is the first element. Now I have written the ones for the first element. What is my second element? The electric field. Now what do I have in the electric field? I am looking at that. Now in my electric field, friends, in terms of direction, where did I say the electric field extends? Its magnitude, its amplitude extends in the z direction. How do I understand that? I understand this because it gives the direction of polarization, which is the s direction. Now please do not write anything here. Just because you see the y component, do not write this box here. This is not the part. As a component, in terms of magnitude, I have to write the electric field component here. I say that I have my e's component as the electric field component. Do not confuse this point. There is only the y component as a derivative. As for the electric field component in this region, since it has an epsilon 0 amplitude, I understand that I have a z component extending in that direction. Therefore I will write this magnitude in this part. So what magnitude will I write? As it is, I no longer need to take the direction vector, because the direction vectors were present here, just like I didn't take them here. Only the common ones were written here. What remains are the magnitudes, meaning whatever is there besides the vector, whatever is there besides the vector, I write the entire E0 times E0jk, so I write all of it except for the direction vector, and since we said it has the EZ component, I write it under Z as a E0 times. E0 times e to the power of minus j. K? Why? So, are there other components in our incoming field? No, I say 0, I say 0. And now, after writing it this way, friends, the point you need to pay attention to here is this. What did I just say? If you take its derivative, with respect to what can you take its derivative? I asked the question, whose function is this, referring to the electric field here? What will you say to me? Of course, it is a function of y. This is the only value I can differentiate here. Y is a component, friends, because right now we don't have a vector operation here. Look, ultimately, these will enter the operation. We are closing this. You know how it is taken, and I will show you, but you know that when we perform operations with the remaining parts by closing them, these will all enter the differentiation process. The only part you can differentiate here is the part related to y, which is the part dependent on the propagation direction. Right now, there is neither a derivative with respect to x nor a derivative with respect to z here. The only thing I took related to z was the magnitude component. And which magnitude component was that? It was the direction in which the amplitude extends, that is, the direction in which the electric field extends. But its differentiability, meaning this amplitude, extending in the z direction, is dependent on the function related to the direction of progression, that is, y. Therefore, the part that can be differentiated is in y. It is based on the direction of propagation, don't forget this, and since there will be no derivative coming from here, I take this part as 0. I also take this part as 0. Just like I took these as 0, why did I take them as 0? Because there are no a and x components of the electric field. I hope I have been able to explain it. Now let me write this down in a more organized way right here. So, can it take this form, friends? After it takes this form, the calculation method is as follows. Friends, first of all, you do something like this. You put a plus, 1, a minus, 1, and a plus. The logic of this plus minus plus is normally the operation that comes from the row and column of minus 1 raised to the first power. Now, since the value of this x is in the first row and first column, when you say minus 1 raised to the first row and first column, its value comes out positive. It comes out as plus 1. That's why a plus is placed here. When you say first row, second column, since it comes from 3 minus 1, it will give a negative result. So these are automatically placed in the form of plus minus plus. Afterwards, doing this operation is not that intimidating. Since there are 4 zeros here, most of them will go away from here. So I can see that probably one of the magnetic field components here will remain. If you want, let's take a look at how we apply this. Let's start with the first one. You do it like this. First, you close the first one. We start with plus, EX. You close it like this. We are closing the first row and the first, that is, EX. After closing EX, we perform the classic determinant multiplication with the remaining ones. That is, we multiply these corners and subtract them from each other. And since I have closed EX, I can write it like this, friends. I say EX times EX, just simply. Afterwards, I say there is a minus 1 over J, omega neuron here. Afterwards, I open a parenthesis like this, and I perform this operation here. I multiply this with that and subtract. And what does it tell me? It says to differentiate E0 e raised to the power of minus jky. I understand this from here. Partial derivative with respect to y of E0 times e to the power of minus jk, I minus 0. So, friends, what does this mean? Very simple. It says to differentiate what? Differentiate this part. Friends, the derivative of this is not a simple thing. Look, what is the derivative of E0 times E0 minus jky? Of course, the ones next to y will come next to it. Hey, let's write that down right away if you want. And since this is EX, then what about the crosses here? I mentioned earlier how to open this cross. I said it opens like this. Who does the 1 in EX correspond to? Automatically. This operation corresponds to EX times HX. So, what can I write on the other side? I can reach the component of EX times HX. You can eliminate EX's from both sides. Generally, we are already concerned with magnitudes. It is sufficient for us to deal with magnitudes. Don't forget this in these questions. Since I specified hx here, you can automatically place ex as the final direction vector. This x here indicates that it is in the direction of ex. Now I say, I will just find hx from here. I will show shortly that nothing else will come from here. I traveled, friends. Ezra Sabit is already here. What will come with him? xgk. Only those next to y fall, you know, and it also comes automatically. Let's simplify here if you want. The minus sign here has simplified with the minus from the classical formula. The j here has also simplified with the j there, friends. And here we reach our hx very nicely. What is hx, friends? E0 divided by omega, nu 0 from here k came. I say there is an e to the power of minus cky combination. Normally this can be continued a bit like this, friends. The k here is equal to omega times the square root of epsilon nu 0. It is equal to the square root of epsilon nu 0. Now if you want, I'll write this right away. Look, you see k here? I will now write this in place of k. Look, I wrote it this way. If you want, let's do the 100 ear here like this right away. I wrote it separately on purpose. Why? Because can I write 100 ear like this? It is the product of 2 times the square root of 100 ear. So I took the square root of 100 ear. As a result, I have to add one more to reach 100 ear again. Therefore, you can see the simplification here. Friends, the omegas also simplified. And finally, let me give you a hint here. The 100 ear here is equal to epsilon ear, friends. This gives us an impedance. The ratio of permeability to permittivity equals a value of impedance called Z0. Therefore, since nu 0 is at the bottom here, I have to write Z0 down like this. Finally, theoretically, it is written like this. hx equals divided by E0. Here, since the square root of n0, y0, z0 equal, I wrote it down like this. Because n0 is at the bottom, and we find it in the form of e raised to the power of minus jkie, like this, friends. So let's see, is our work done yet? No. When you look from here, friends, what did we close here? We had covered ex. If you like, let's look at the others right away. When you cover ey in this area, what do you see, friends? It will start with minus, be multiplied by ey, and the remaining ones will be multiplied and subtracted. Look, since 0 times this, minus 0 times this comes, what can I automatically say here, friends? I can say it's hy0. And, finally, who should we cover? Let's cover z. Who are the remaining ones, friends? These two are 0 minus del over del I multiplied by 0. So, who did we cover? It was ez related to ez. Of course, we can automatically understand this, so we find ez as 0, friends. This is how we expand the Maxwell equations. Here, it will depend on both x and y. Let's say you write the equation here. You would also write the x component here. The differentiation will depend on both x and y. You would write del over del x. So, this is how you will perform the operation. The determinant is expanded this way, friends. What did I say at the very beginning? Pay attention to the H2's incoming magnetism. Let's explain the logic. Here, right away. I mentioned it a moment ago. Now, the direction of the electric field is in the z direction, and the direction of progression is in the positive y direction. Z was used, and y was used. Since the electric field, magnetic field, and direction of progression are all perpendicular to each other, and from these three directional vectors, I only used z's for the electric field, and y for the direction of progression. I was probably expecting a magnetic field to remain, and as you can see, I was expecting the X compound to be the magnetic one, and be careful. So, where could we find the magnetic field, meaning just the magnetic field? Not for y and z, but in this way, for x, and we found its magnitude in this way. Does it make sense for it to be e to the power of minus jky? Of course, because in which direction is the incoming electric field propagating, friends? Saying minus jky means in the positive direction, of course the electric field must propagate in the same direction, because their propagation directions, that is, their directions of progression, are the same. Both of them together, because they are both propagating in the same direction at the same time. That is, they are propagating in the positive y direction. That's the essence of the matter, friends. In another way, I wanted to give you the foundation, piece by piece in at least 3 separate videos, as we have established it this way. First, the boundary conditions, then Helmholtz's solution and logic, and after understanding the expansion of Maxwell's equations, I hope that even if you encounter different types of questions, you will at least have an idea in your mind. Thank you for listening. I hope to meet you in another video. Goodbye.